I will share this. Okay, so you have done the assignment. Yeah, you have done the assignment about the octa number, the zeta number, and also about the machine to test it. Yeah, to test the octa number. Now, before we go on that discussion, so we will take a brief look at the explanation of what are the combustion stages in the spark ignition engine. Yeah, and we have learned this last week as well. So I will just do a brief review on this, in which we have the pressure here as a function of crank angle, and we see here that there is an increase in pressure, yeah, during the process in the cycle. So what we have here is that when we have a compression stage, when we have a compression stroke, yeah, or a compression process, so that the pressure will increase. And afterward, before it reaches the top dead center, the spark ignite. And what happened is not automatically burn on the fuel inside, but it needs some time. So this is called the ignition lag. So we see here that we start the spark to ignite at about this point, which is at point A, and then it start to burn at point B. Yeah. So the burning process, it starts on B, point B. So there is an ignition lag. And afterward, there will be a propagation of flame so that it will increase the pressure to a maximum here at point C. And afterwards, we will have the afterburning process, in which this will be the expansion process or the power process in the cycle. Yeah. So these are the stages in SI engine. Yeah. And we have seen the explanation here relates to the point, yeah, which is from A to B is the ignition lag, yeah. So point A is the spark plug ignites, which is about 28 degrees before top dead center. Now this is not a strict value, yeah, but this is depends on the engine and as well as the rotational speed of the engine, yeah. And we have point B here, in which the pressure start to increase. So this means that the fuel is already burned, yeah. And then point C, we will have the maximum pressure, yeah, the maximum pressure. And afterwards, we will have the afterburning process, yeah. So we see here that we have the ignition lag. So what happens in the ignition lag is that we have the preparation stage, or we have the delay of the burning. Yeah, so this depends on the chemical process, depends on the fuel, the temperature, the pressure, yeah, or and also the exhaust gas proportion and other factors. And from point B to C, which is the flame propagation, as we see in here, in which it will reach the maximum pressure. It is a mechanical process, so we will see that this is a burning wave, yeah, and this starts at the point of increasing pressure, which is started from B up to the maximum pressure. So we will see here how it looks like. So we have a photograph taken in the combustion chamber, yeah, in which this is the area of the top dead center, yeah. So this is the clearance volume, yeah, the clearance volume here. So this is when it reaches the top dead center here. Yeah, so we see here that after intake, the fuel air mixture is compressed. So we have a compression process here when in which the piston moves to the top, yeah, and then before it reaches the top dead center, it's already ignite. Yeah, it's already ignite. So we see here that this is the photograph which is taken at point A. Yeah, so we see here that the spark plug here even it even start or ignite before 28 degrees. Yeah, before 28. So we see here is quite far, which is before 40 degrees. So this is the spark plug ignition, and then A here we already have a small burning here, which is at point A, and then B, it's increasing, yeah. So we see here that it's now already burning, and C here, yeah, started to increase, and this is point D and E, yeah. So this is the maximum pressure, and then this is the after burning process. So we see here that this is like a flame wave, yeah, from the point close to the to the spark plug further away to all the area inside the cylinder, yeah, inside the clearance volume of the cylinder. And we see here that it's an expansion process, yeah. So we see here that it's point D is actually the top dead center. So if we look at here, the area here, yeah, the volume here is the smallest. So D here is at the top dead center. And afterwards, it will have the process stroke, yeah, the process stroke, the power stroke. So it's the clearance volume here, the volume becomes larger, yeah. So this is the example of the figure. So in ideal case, we will have the flames starting from the spark plug, yeah, very close to the spark plug, and then it will propagate away from the spark plug to another area, yeah, to fill in the volume. Now, this is relates to what we discussed last week, which is about knocking. Yeah. So I will. So this is a flame development. Yeah, development of the flame in which we have a flame development, and after that we have the rapid burning angle. Yeah. So we have a at the first instance. Yeah, at the first instance, the flame here start very slow, and then afterwards it will have a rapid burning process. Yeah. So that the overall burning angle will be the total. Yeah. The sum of flame development, and rapid burning angles. Okay. So when we look at here, what is the correlation between the burning time and the engine speed? Yeah, so this relates to the rotational speed of the crankshaft. Yeah, it means then when we have a higher engine speed, so that the stroke will be faster. Yeah. So that the question is, how does the flame burn all the mixture in the cylinder at high engine speed? Because it's going to be very fast. Yeah, it's going to be very fast. And this one thing that we should consider is that there will be an ignition delay in the process. Yeah. So if you look at here, how is the analysis if we have high engine speed? So we look at here that piston speed is directly proportional to the engine speed. Yeah. So if we have an engine speed or the crankshaft's rotational speed, that will be proportional to the piston speed, yeah, or of the movement of the stroke. And when we have higher piston speed, it means that when we talk about combustion, we will have flow inside. Yeah. And when we talk about flow, so this will relate with fluid as well. Yeah, the fluid flow. And so that if we have higher piston speed, it means that we will have higher turbulence intensity. Yeah. So yeah. When we talk about turbulence intensity, so of course this is dealing with turbulence flow. Yeah, this is dealing with turbulence flow. So when you learn about fluid mechanics, yeah, we know that the flow can be laminar or turbulence. And when we have the turbulent flow, it means that we will have more mixing. Yeah, turbulence flow means more mixing, chaotic movement. Yeah, chaotic particle movement. So it means that when we have a chaotic particle movement, it means that the mixing will be higher. So that when the mixing is higher, so what happened with the burning process? Yeah. So that when we have the turbulent intensity increasing, yeah, when we have the turbulent intensity increasing, so it means that the mixing, yeah, the mixing is increasing as well. Yeah. So when the mixing is increasing, so that the turbulent burning velocity is also increasing. So that when we have higher engine speeds, yeah, when we have higher engine speed, it means that the turbulent velocity will be higher as well. And because the turbulent velocity, the turbulent burning velocity will be higher, or the flame velocity will be higher, it means that it will need less time to burn the entire mixture. So this is fortunately, yeah. So if we have a higher engine speed, so that causes the turbulent flow inside the cylinder. Yeah, when the turbulence intensity increases inside the cylinder, so that means it will be burned faster. Yeah, so in this case, this is a fortunate for us. Yeah, so that there will be no problem. Yeah, no problem. So because we have a higher flame velocity. So that what happens with the combustion duration, as we see before that, we need an overall burning angle, which is a summation of the flame development and also the rapid burning angle, so that the total will be the overall. So what happens if we increase the engine speeds? We see here that some studies have suggested that it will increases only a small amount, yeah, of the crank angles. Yeah, so the total crank angle requires for the burning process will be more or less similar. Yeah, more or less similar. Although we are using low speed engine, or we operated at higher engine speed. Yeah, so this is the comparison. Yeah, so we see here that yeah, there is a little bit of increase, yeah, of course, here when we increase the engine speed. Yeah, so the total crack angles required for the system, yeah, will a little bit increase here. Yeah, so this is something to be controlled as well. Yeah, that's why we have the engine controller unit. Yeah, in which that will adjust. Yeah, that will adjust the crank angle duration here when to start to the ignition, yeah, and also to control the opening of the inlet and exhaust valves, yeah, and that will depends on the engine speed. Yeah, so this is a brief explanation of how the combustion process will differ when we have different engine speed. Okay, so that because we now understand that the turbulent flame velocity here will depends a lot on the turbulence intensity. Yeah. So when we want to have a better combustion process, faster combustion process, it means that we need to have higher flame velocity. And that means what we can do is that to achieve that is to increasing the turbulence intensity. So that's why we often design a cylinder. Yeah, we often design a cylinder so that it will increase the turbulence intensity inside. Yeah, so this is also relates to the design of the cylinder. Yeah, so why we have the exhaust and inlet valve is usually positioned at a certain angle. Yeah, so if we have a piston, yeah, we have a piston, and then we have the head of a piston like this one, and we have the valve here. Yeah, so usually the valve is directed at a certain angle. Yeah, so it's not like this one. Yeah, it's yeah, it is possible, but it's better to use this in which the valve is located at a certain angle. So what is the purpose of this one is to introduce the turbulence intensity, yeah, to increase the turbulence intensity, because if we give an angle here, so there will be a swirl inside the cylinder. While this one, we don't have the swirl is minimum, so this one will increase the turbulence intensity. Yeah, so this is related to the design of the cylinder. Yeah. Okay. So that when we look at the process of the burning, yeah, inside the cylinder, so we see here that during the combustion, the cylinder volume is very narrow, yeah, which is very close to the top dead center. And we know that based on the explanation before that, we have the propagation of the flame to the surrounding here, starting from the spark plug. So we will have like this one, yeah. So starting from the spark plug, and then it will propagate away from the center. So there's very important now to look at the heat loss, because when we discuss about heat loss, yeah, this is also the cause of an efficiency, yeah, efficiency reduction. Okay, so we see here that head loss to the piston and cylinder head is very important. How if we want to reduce the heat loss so that the efficiency will become higher? Yeah, if we want to reduce the heat loss, it means that we want it to have a very small burning time or high flame velocity. Yeah, so if you look at this, how to minimize the heat loss is that by either increasing the laminar burning velocity, yeah, or increasing the turbulence intensity. So this is what we have discussed before, yeah, how to increase the turbulence intensity. If it's possible to make it turbulence, so we want to make it turbulence, and we can design the cylinder such that the flow inside will be turbulence. Yeah, or if it's not possible, so that if we have only laminar flow, it means that we have to increase the burning velocity, or try to operate it at higher speed. Yeah, at higher speed. And yeah, and we have seen that this relates a lot to uh, the power performance. Yeah, we see before we have power as a function of rotational speed. Yeah, we know that we will have a maximum later, yeah, at some point here, which is the optimal operating speed. At very low here, the power is low. Yeah, the power is low because we have high heat loss here. So this is dealing with this. And we see here that if, for example, we have to operate it at very low rotational speed here, how can we increase this one? Yeah, because the speed of the piston is already slow. Yeah, and how can we increase the burning velocity? Yeah, so we see here that when we want to reach that, so that it means that we have to change the composition, yeah, the composition of the mixture, so that if we want to have higher laminar burning velocity, so that's aside from increasing the piston speed, what we can do is that we change the composition so that it will become slightly rich mixture. Yeah, slightly rich. So a richer mixture, it means that we give more more fuel. Yeah, more fuel. So this is to increase the laminar burning velocity. So this is one thing we can do. Yeah. So either increasing the piston speed, or if we cannot increase the piston speed, so what we can do is that we control the mixture so that it becomes richer. Yeah. Okay. So this is dealing with heat loss. So that yeah, relates to that. Yeah, it relates to this one, so that we will have the fuel air composition. Yeah, the fuel air composition, in which we have the equivalence ratio, in which we have discussed that before. Yeah, in which the equivalence ratio here is the ratio between the fuel air ratio of the actual over the fuel air ratio of the stoichiometric. Yeah, over the stoichiometric. So if we have a value of equivalence ratio greater than 1, it means that we have rich mixture. Yeah, it means that we provide the fuel beyond of that required in the stoichiometric reaction. And if we give less here, yeah, we will have a lean mixture. And we see here that yeah, when we plot this one, PSFC, yeah, so we have here that the brake specific fuel consumption here will have the minimum value, which is around here. Yeah, so this is the minimum value. And if we look at here, the minimum value is not exactly in 1. Yeah, so not exactly of what we have calculated in the stoichiometric reaction. Yeah, but instead of on the actual case, yeah, when we tested that, we have a lean mixture, yeah, that give the best specific fuel consumption. Yeah, so less than 1. Yeah. Okay. Right, so this is about the fuel air composition, yeah, which relates to the burning process. And also this is dealing with spark timing. Yeah, again, with spark timing, this will depends on, this will depends on the engine as well. Which when we have to start the spark to ignite, yeah. So we see here that we can, it depends on the operation. Yeah, we can start it, this, for example, in here, we start at 10 degrees, yeah, about 10 degrees before it's reached the top dead center. And also it can be 30 degrees before the top dead center, or even up to 50 degrees before it reach the top dead center. Yeah, and what affect this one, this really depends on the engine size, yeah, and the speed, yeah, as well. The overall burning angle, as said before, is between 40 to 60 degree. Yeah. All right. And this is also dealing with MBT, maximum brake torque. Yeah. In which the optimum spark timing, which gives the maximum brake torque, is called the MBT timing. So if we have the words of MBT timing, it means that when we start the spark plug is to achieve the maximum brake torque. Yeah, to achieve the maximum brake torque. Okay. And this is the comparison. Yeah, the comparison for the brake torque, which is obtained from several rotational speed. Yeah, so we have different rotational speed here. And this is operated at a wide open throttle. We have, 1200 and so on. Yeah, in which this will have different spark ignition. Yeah, as the spark advance. So how many degrees before it reaches the top dead center. So it really depends on the rotational speed as well. Okay, and this is the combustion reaction. I think we have discussed that last week. Yeah, so this is just a review. And we have seen that the performance chart. Yeah. So overall, we have the power will increase and then it will decrease again. Yeah. EMEP and PMEP, that will depends on the power also. And friction power will be the subtraction from the brake power to the indicated power. Right. So that will be the review of what we have learned last week, which is about the combustion process. Now we've discussed about knocking, and we have a parameter for the fuel in which we have done that in the assignment, in which this relates to knocking. Yeah, and we already learned about knocking before, in which it's occurred because there is a localized auto ignites at other area or other volume in the cylinder, so that when we plot the pressure, yeah, as a function of the crank angle, so we will see here that in normal operation we will have a smooth pressure increase and decrease like this one. But when we have knocking, so then we will have a fluctuation in the pressure. Why this is happening? Because we have the other area which is burnt locally, so that will increase. That will cause some increase in a certain crank angle. So we have unsmooth operation like this one. Yeah. So this is basically generated by shock waves in the cylinder. Yeah. So if you want to look what happened here, so that we can see, this is the normal one, yeah, in which that will start from one point to another, yeah. And here we see that if we have a knock cycle, yeah, so we have a fluctuation in the pressure. So we'll see here that it's not smooth like this one, the propagation of the flame, yeah, but instead we have local flame on the surrounding, so it's not as smooth as this one. Yeah, so we have many local burn on the sides, yeah, of the cylinder. Yeah, so this is the illustration in which when we have the normal operation, so the flame will propagate from the center, which is from the spark plug to the surrounding. But in shocking, yeah, when the flow propagates, so then we will also have some auto ignition, yeah, of the fuel outside of the flame wave, yeah. So that will causes fluctuation. Now, this relates to, yeah, some parameters. Yeah, some parameters. The first one is relates to the compression ratio. Yeah. Um, if we have the pressure and the temperature is too high, yeah, we have the operation of the temperature, the operating pressure and temperature is too high, so that may cause auto ignition. Yeah, because we know that fuel becomes more, is easy to burn at high pressure and high temperature. And also the engine speed. Yeah. When we have low engine speed, yeah, when we have low engine speed, so that the flame velocity will be slow. Yeah, the flame velocity will be slow, so that the burn time is long. So that what happens when it's too slow, if we have high pressure and high temperature, so the other places here may auto ignite. Yeah. And also this is dealing with spark timing. So maximum compression from the piston advance occurs at top center. Yeah. Increasing the spark advance make the end of combustion crank angle approach the top center and thus get higher pressure and temperature in the unburned gas just before burnout. Yeah. So if we set the spark timing too advanced, yeah, if we set the spark timing too advanced, it means that during the process, it will increase the pressure, yeah, it will increase the pressure before, yeah, before it's really burned, yeah, the pressure getting very high, yeah, getting very high because it's also compression, yeah, and that will cause the unburned gas will auto ignite. Yeah, so this is a problem when we don't set the spark timing correctly. So yeah, these three factors may affect knocking. Yeah, and this will relates also to the fuel. Yeah, and this is the assignment to you, which is about octane number, certain number, and the engine to test it, which is called the cooperative fuel research engine. Okay. Now, before we discuss of this, maybe one of you want to discuss of what you have found from your research for this assignment. The first one, which is about octane number. Well, yeah. So what you found about octane number? What did you have found? What have you found? Yeah. About octane number.
All right, speaking ma'am.
Yes, Sultan.
I want share my homework to you and the other friend. So what I found about octane number is the percentage by volume of isooctane reside in the mixture of isooctane and heptane. So this is a ratio, ma'am. Ratio about mixture of isooctane with plus n heptane. And octane number is for gasoline engine, for gasoline, so is kalau di bahasa Indonesia bensin, because for diesel is certain number. And then what is isooctane? Isooctane is the ideal fuel, so it is it has 100% octane number, and N-heptane is the strike hydrocarbon chain that it has near zero value of octane number. And what I found about the strike hydrocarbon, and I found something about the strike hydrocarbon effect for the octane number. So when the length of straight hydrocarbon chain is higher, so the octa number value will drop because straight chain hydrocarbon is N-heptane. So when we have more straight chain hydrocarbon, so it will have more knocking in the engine. And how to decreasing the knocking or how to increase the octane number, we could add some aromatic hydrocarbon like because aromatic hydrocarbon is such isooctane. So when we want to increase the octane number, so we could increase the aromatic hydrocarbon or making the molecular structure of the fuel more branched than before, ma'am. So we change, so we make the hydrocarbon structure not straight, but we make it branched. Okay. Like that, ma'am.
All right. Okay. Yeah. So yeah, it is correct. Yeah. It's about when we talk about octane number. So this is relates to knocking. Yeah, relates to knocking, and this is said to be that there is a composition inside the fuel. If we have pure isooctane, so that will be the ideal case in which we will have an octane number of 100. Yeah, and if we have a pure N-heptane, so that we have an octane number of 0. So what we want to expect is that we want to have a high octane number for the fuel. Yeah, and yeah, this is relates to the molecular structure in which you have a straight chain or straight chain. Yeah, for the molecule, or whether you have a branch for the molecules structure. Yeah, and yeah, so this is correct already. Anyone any other perhaps the other one to add? Yes, Angata.
I want to ask about the isooctane and heptane ratio here. So I think there is some fuel that doesn't contain isooctane or N-heptane or contain that, but in a with ratio such as maybe if you know an E85, a mix of gasoline and ethanol, it has a higher octane number, I think, above 100. If this ratio of isooctane and heptane still relevant to measure octane number?
Yeah, so can you repeat the question? If we add ethanol, for example, so it will be above 100, is it?
Yeah, kind of like that. So is the ratio of isooctane and heptane still relevant to measure the octane number?
All right. Yeah. Okay. So we will see about the explanation of octane number before, and also what have been mentioned before is also that what we can do is to increase the octane number is by giving an additives. Yeah. So we will discuss about that as well. So by giving additives. Yeah. All right. Okay. So yeah. We will see a brief explanation on this one. Yeah. Now we will keep on that first. Yeah. So the first question, we will discuss certain number later. Yeah. Because we still discuss about gasoline engine or spark ignition engine. Okay. So we will look at the explanation here. Yeah. So octane number is actually the ability of the fuel to resist knocking. Yeah, to resist knocking. So this is a quantity, yeah, to show the ability of the fuel to resist knocking. So that the octane number determines whether or not a fuel will knock in a given engine under given operating conditions. So that, yeah, it is correct. that the higher the octal number, the higher the resistance to knock. So that as mentioned before, that isooctane has a value of 100, yeah, and normal heptane or N-heptane has an octane value of 0. So that how can we say the value, yeah, whether the octane number is 90 or 80, for example, yeah. So that depends on the blend or the composition of these two hydrocarbons, yeah. So in general, like this one, yeah. So in general, like this one, so that this will define the knock resistance of intermediate octane number. So for example, if we have a composition of 10% of N-heptane and 90% of isooctane, so that the octane number will be 90. Yeah. So that a fuel's octane number is then determined by measuring what blend of these two hydrocarbons matches the fuel's knock resistance. Yeah. So that why we have that cooperative fuel research engine. Yeah. In which this is actually using the single cylinder engine. Yeah. And this is a 4-stroke engine, and the dimension is already specified here. This is a bore diameter, and the stroke step here is 4.5 inch, and the compression ratio can be varied from 3 to 30. Yeah. So this is the engine. And then we can perform two methods in the engine. Yeah, so there are two methods can be performed in the engine, because we can vary the compression ratio can be varied, and also we can vary the speed. Yeah, we can vary the spark timing. So that here we have two method, which is we have the RON or MON number. Yeah, RON here is stands for research octane number, and MON is for motor octane number. So what is the difference is that the operating condition is different. Yeah, so the operating condition is different. For research, for getting the RON value, so that the inlet temperature is 52 degrees, while for MON we have 149 degrees Celsius. And the rotational speed is different. Yeah, the engine speed is different. The spark timing is also different. So spark advance here different. Yeah. And what about the coolant temperature and the inlet pressure is kept constant. Yeah. And the humidity, yeah, so that can be used at this range, but more or less similar. So that with different temperature, different inlet temperature, yeah, and different speed, so that we find out that the motor octane number is always higher because it uses more severe operating conditions. Means that it's using higher inlet temperature and more spark advance. Yeah. So then when you tested whether RON or MON, so what we have as an octane number, yeah, the MON value will be higher than RON value. Yeah, so this is just for knowledge for you. Yeah, so that what is the testing procedure? We run the engine, yeah, at both research and motor condition, and then we slowly increase the compression ratio until a standard amount of knock occurs as measured by a measurement device, which is called magnetostriction knock detector. Yeah, so this should be calibrated at first. Yeah, this should be calibrated. And that compression ratio run the engines on blends of heptanes, N-heptane, and isooctane. Yeah, so that when we have the octane number, so then it's defined by the percent of volume of octane in the blend that produces the stand. Yeah, so then when we already run that, we will have the value of RON and MON at different value, so that the anti-knock index here, yeah, the average octane number, yeah, the octane number or the anti-knock index will be the average between the two. Yeah, so the average between RON and MON. Yeah, so this is to obtain the value of the octane number. So that when we add another, yeah, when we add another, yeah, we can add additives, yeah. For example, we can add lead, for example, although this is not suggested because lead is not good. Yeah, but we can add, for example, additives to the fuel so that this can be measured, yeah, in the engine and see the comparison with what happens with the if we have 100% or pure isooctane. Yeah, so that answering your question. Yeah, answering your question. Yeah, we cannot when we add the additives here, we cannot use again the comparison of the composition, yeah, or the ratio of the composition between isooctane and heptane. But what we see is the relative performance, yeah, the relative effectiveness. So the maximum value will be 100 still, yeah. So when we add this, yeah, for example, these additives to the fuel, yeah, so the maximum value which is 100, yeah, although it cannot be calculated using the composition as shown by this one. Yeah, it cannot be calculated as the composition shown by this one, but we compare the NOx index, yeah, which is similar to 100% of octane, yeah, isooctane. Yeah, so that we tested in this engine and see how what is the value measured by this detector, yeah, by this measurement device, so that the maximum will be 100. Yeah, the maximum will be 100. Okay. Yeah. So I think that will be yeah, that will be the explanation. Yeah. All right. Okay. Is there yeah?
So if I understand, please correct me. From my understanding that we can use whatever kind of fuel, but the performance will be compared to the fuel tested using the CFR engine. Like
Yes.
for example, if we use a fuel that have no relation with isooctane, but when tested, it have the same performance as fuel with 90% isooctane, for example. So it will be around 90.
Yes.
Oh,
Yes.
thank you, ma'am.
Yes. Yeah. 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 So that is the function of the engine. Yeah, the function of the engine to test it whether if you want to use additives as well. Yeah. How is the performance? So we tested using that engine and compared whether that value, yeah, what is that relative value to the pure isooctane, which is 100, yeah, which is the ideal one, which is 100. Yeah, yeah. All right. Any other question?
Excuse me, ma'am.
Yes.
Can I ask about something, but it's maybe previously, ma'am.
Yes.
Okay, about the laminar burning intensity, ma'am. We can increase it with slightly rich mixture control, right, ma'am?
Yeah. So here we have which one is that laminar? Yeah. Before. Yeah. Laminar burning velocity. Yeah.
Yes, ma'am. So we can approve it with slightly rich mixture, right, ma'am?
Yes.
Then how we can control the slightly rich mixture?
Yeah. Yeah. So to control this one, yeah. Maybe I should check again. Yeah, but usually this is control in the engine controller unit. Yeah, all of them for especially for the newer car. Yeah, we have the ECU in the engine, so that can control whether we want to have a slightly rich mixture there. So we can control the opening, yeah, the opening of the throttle or the injection of the fuel. Yeah. Yeah. So that is from what I from what I think. Yeah. So I will check again. Yeah, I will check again. But usually the balance, yeah, or the balance or the control for everything in the engine is in ECU. Yeah. So we can define, for example, for a certain speed, when is the the camshaft opening for the valve, yeah, as well as when the spark plug timing and how much is the composition or the injection, how wide is the throttle opening and so on. That is all controlled by the ECU, yeah, the engine controller unit. So yeah, so that it's ECU is very important, yeah, because we will have a wide range of rotational speed, engine speed, yeah. So that will be set for every rotational speed, so that when it's operating at lower speed, yeah, lower engine speed, so that it will control the mixture, so that it will becomes richer, yeah, and so on. When it is when the engine speed is increasing, so that it will also control the composition of the mixture as well. Yeah, so it becomes leaner, for example, and so on. So that I think, yeah, it's all integrated in ECU. Yeah, and therefore, yeah, yeah, if you interested in that, yeah, we have. Yeah, we have many undergraduate students who work with Pak Bambang Sudarmanta as well, yeah, and Pak Ato as well, yeah. Previous years ago also tested the control of in ECU, yeah, to control the spark timing. So when to start, and also, yeah, to control the opening of the inlet and the outlet valve and so on, yeah. So yeah, I think that will be controlled in ECU as well, yeah.
Okay, ma'am. Alhamdulillah, I get it. Thank you, ma'am.
All right. Thank you, Edgar. Yeah. Any other question? All right. If there is no question, so that will be an explanation of SI engine, yeah, SIE engine, or about gasoline engine. Now we will continue on the next question, which is about SETA number. Yeah, we have learned, we have done some studies on SETA number for the assignment, and we will discuss about that. So when we talk about SETA number, so this is dealing with diesel engine. Yeah. Now before we have a discussion on that, so we will see how the diesel engine works. Yeah. We already learned about that we already learned the cycle, yeah, the diesel cycle, but I will stop this first and we will continue to the second slide. Okay, so we are going to talk about diesel engine and also the dual cycle engine. Yeah, you have learned both in thermodynamics, yeah, the second thermodynamics. And what is the difference between gasoline and diesel? I think, yeah, it's almost similar. In diesel engine also we have 2-stroke and 4-stroke engine, and we have the same cylinder, for example, almost the same cylinder, yeah. But the difference is that the compression ratio is higher in the diesel cycle. And when we look at the cycle, actually the cycle is different, yeah. So what is the difference is that, yeah, from the cylinder, yeah, let's see the difference here. From the cylinder is almost similar, yeah. It's almost similar. We have the cylinder, we have a piston in which the piston will move down and up, yeah. Now the difference is that the compression ratio should be higher, yeah, in diesel cycle. And also, can you mention the difference between diesel and gasoline aside from the compression ratio? Regarding the process, we have discussed that last week as well.
The injector, maybe, ma'am.
Yeah, the injector. Yeah. What is the difference? Here we have the fuel injection. Yeah, so we have the fuel injection. It means that the fuel is not mixing with air before it goes into the cylinder. Yeah, but instead the air is compressed and then the fuel is injected. So in this case, we don't have the spark plug. Yeah, we don't have the spark plug. Yeah. Okay. So another different, is that another different to the gasoline auto cycle?
Plug is for exhaust only.
Yeah, we have the plug for the exhaust only. All right. Okay. Any other? So we have already 3 different then. Again?
Maybe it is about the first induction of the air intake, ma'am.
Mm-hmm. Yeah. What is the different, the induction?
I think the air intake is forced with blower in the diesel cycle.
Mm-hmm. So there is a blower, yeah, in the diesel cycle. Yeah. Yeah. So yeah, usually we have a blower, or when we have a diesel cycle, it's more common to have turbocharger. Yeah. So we often use turbocharger or blower here. Yeah. In order to get more air. Yeah. Such as one as this one. Yeah. So yeah, we have a 2-stroke diesel cycle and also 4-stroke. Yeah, more or less this is similar to gasoline. Different, similar. It means that 1-stroke here, first stroke, we have 2 process. The intake, the first stroke here is the intake and the first stroke here is the intake and then compression. Yeah, so it's going up. First intake from the bottom that's centered, we have an intake here, and then it start moving up. So we have a compression, and then afterwards we have fuel injection. So we have a burning process, and then afterwards we will have a power stroke. Yeah, and afterwards we will have the exhaust gas goes out. Yeah, here. Yeah. All right. And we have 4-stroke engine. Yeah, we have 4-stroke engine. And the process is similar to what we have in the gasoline engine. So we have intake, compression, power, and then we have exhaust. Yeah, so similar to gasoline engine. The difference is that now we use fuel injection instead of spark plug. So to make sure that this fuel will be burned when it's injected into the cylinder, we have to make sure that the pressure is very high. Yeah, the pressure is very high inside the cylinder. If the pressure is not high enough, so that this fuel will not be burned when it's injected. Yeah, so that's why the diesel cycle here requires higher compression ratio. Okay, and because it has higher pressure ratio, higher compression ratio, so that usually the temperature is hotter. Yeah, so that we have to provide a sufficient cooling here. Yeah, and also here we have a turbocharger as we have discussed before. Yeah, to provide the fresh air into the cylinder. Yeah, so here in this example, this is 4-stroke engine. Yeah, so we have the turbocharger here in order to give more fresh air, yeah, into the cylinder so that it can reach higher pressure ratio. And usually from the turbocharger here, the temperature is already a little bit higher. Yeah, and here we have a fuel injector, and this should be supported with a fuel injection pump. So we have a fuel injection pump here. Yeah. All right. So the rest, yeah, more or less almost similar. Yeah. Okay. So the diesel engine here can be used for automobile, or also it can be used for generator. Yeah. So this is an example of diesel generator. It means that we can use that in diesel power plant. Yeah. In diesel power plant. And this is the cycle. Yeah. And this is the main difference when we look at the cycle, when we compare that with Otto cycle. Yeah. So now we have the cutoff ratio in which we have discussed before. Why? Because we have the fuel injection and the combustion process. It means that the heat addition now is not occurring at the constant volume. Yeah, it's not occurring at the constant volume. Instead, the combustion process occur at constant pressure. Yeah, constant pressure or isobaric process. Yeah. Now, this is the main difference between the diesel cycle and the Otto cycle. So if we have the ideal cycle here, so what we have here, we have isentropic compression and isentropic power stroke here, or isentropic expansion. Yeah. And we have here the exhaust, yeah, and we have here the burning process, yeah, or heat addition at isobaric. So isobaric heat addition and isochoric heat release. Yeah. Now, what if we look at the actual cycle? So there will be a little bit of change here, yeah, in which we will have the intake and exhaust stroke, yeah. So there is approximately isobaric, but we have probably a little bit of changes of pressure here, but it's not significant. And afterwards, we will have the compression, which is adiabatic compression, yeah, but not following exactly the isentropic line. And then we will have fuel injection. And in actual case, the fuel injection is not performed at 2. Yeah. Again, almost similar in gasoline engine, in which we have to perform the fuel injection slightly before. Yeah, slightly before. So we injected the fuel here before it reaches the top dead center. Yeah. So that afterwards we will have heat addition. And then we have the power stroke here, and then the exhaust valve open at 0.4 here, and then so on. Yeah. So this is the actual diesel cycle. Yeah. Okay. So we can draw that cycle in PV diagram as before, and also in TS diagram. So this is for the ideal case. Now, if we have the dual cycle, yeah, if we have the dual cycle, so the dual combustion cycle will be a sort of a combination between the two, yeah. So if we have the dual cycle, so there is a combination of the Otto cycle and the diesel cycle, yeah. So if you have Otto cycle here, it had heat addition. Heat addition is occurring at constant volume. And in diesel cycle, heat addition is occurring at isobaric. So in dual cycle, heat addition here occur at this area. Yeah, so this area. So we have two processes here for the heat addition. So we have isochoric and isobaric process for the heat addition process in dual cycle. Right. Now we will discuss the diesel engine first. Yeah. Now before that, if you want to know what are the application of dual cycle, yeah, dual cycle is typically used for low speed marine diesel engine. Yeah. So we know that the marine engine, yeah, and also if we have submarine, yeah, submarine is using diesel. Yeah, sometimes it's using diesel. Yeah, if it's using diesel, so this diesel is actually, it's not pure diesel, but we have a dual cycle. Yeah, a dual cycle. Right. Now we will see on the efficiency that we have from the thermodynamics. Yeah, we will not discuss about this again because you have learned this in thermodynamics, but we will see how the combustion process in diesel engine. Yeah, so this is the theoretical efficiency, the thermodynamic efficiency of a diesel cycle. Yeah, and R here is the compression ratio, and RC here is the cut-off ratio. So you can use this formula to calculate the thermodynamic or theoretical efficiency of the diesel, yeah, diesel engine. Thermal efficiency, yeah, so this is okay. And this is using undercooled air standard assumption, yeah. Okay, so when we look at the combustion process in CI engine or compression ignition engine, so that we have the fuel here, which is sprayed. Yeah, we have the injection of the fuel into the cylinder. Yeah, so we see here that when we inject it, yeah, and then the fuel air mixture ignites spontaneously. Yeah, so that we see here that we injected the fuel, and about 0.4 milliseconds after ignition, we already see here, yeah, there is an ignition here, and 3.2 millisecond after ignition, this would be larger, yeah. We see here that we still have the injection here, yeah, we have the injection, and we have a large flame here developed, yeah, and so on. So this should be there, here, and here. And this should be at slightly larger time. And late in combustion process, when it's finished with the combustion, so it's start to, start to finish, yeah. So this is when the fuel is already burned, yeah. So this is the burning process in combustion ignition engine. So when we plot this in, when we plot the process in pressure to crank angle, as what we have performed in the gasoline engine before. Yeah, so we see here that in general this will be similar. Yeah, the trend will be similar, and also we will have a sort of a delay that we have in the spark ignition engine. Yeah, so we see here that we have the top dead center will be at this point. Yeah, will be at this point. So when we start to inject the fuel, we will do it slightly in advance. Yeah, so usually here in this example, we give about 18 degrees before it reaches the top dead center. Yeah, so we see here that it will start the injection. Yeah, start the injection. This is the injection, and this after that, yeah, because we still have the movement of the piston here, so the pressure increase, and afterward this is the start of the combustion. When the combustion starts, so then we have a very sharp increase in pressure, yeah, and it is expected that the maximum pressure will be reached when it's at the position of very close to the top dead center, yeah, and afterwards it will go down. Yeah, so we have several stages here. We have the first phase here, which is from start of injection to the start of combustion. This is phase 1, and then from phase 2 to phase 3, in which this is the start of combustion to the maximum pressure, and then 3 to, yeah, from this 2 to 4 here we have we have a decrease in pressure, or as this is as a power stroke. Yeah. Yeah. So we will see here that, yeah, we have the 4. Yeah. Basically, we have 4 phases there. Now we have the first stage here. Yeah. So 1, 2, 3. 3 here is already go down, and then 4 here further. So we have the first stage here, which is the ignition delay. Yeah. This is called the ignition delay. So very similar to what we have in gasoline engine, in which fuel is injected directly in the cylinder, very close to the top dead center. And then what happens here when there is a delay is that the liquid fuel, yeah, the liquid fuel atomize, because what we have here is still in the form of liquid. So when it's injected, it will be atomized into small drops, into droplets, yeah, into droplets. So initially it's in the fuel flow, yeah, as a flow, as a continuous flow, then it's atomized, becomes droplets, and then it penetrates into the combustion chamber. And afterward, it will have a mixing, yeah, the fuel vaporize, yeah. So there is a process of atomization into droplets, and then vaporization and mixing with the air, yeah. So there are 3 basically three mechanisms occurring in the ignition delay. Yeah. And afterward from and phase 2, next is the premix combustion phase. Yeah. So the premix combustion phase here is already the combustion process. Yeah. So this is already the combustion. So this is the start of combustion, in which it will increase the pressure, sharply. Yeah. Increase the pressure sharply. So this is the combustion of the fuel which has mixed with the air to within the flammability limits. Yeah. Or air at high pressure and high temperature during the ignition delay period occurs rapidly, yeah, in a few crank angles. Yeah, so this is a pre-mix combustion phase. Yeah. Yeah, so what happens here? We have a combustion phase for the fuel that has been mixed with the high pressure air which is occur in the ignition delay. And afterwards, we will have the third phase, in which this is after the peak pressure. Yeah, after the peak pressure. So we have here after the premix gas consumed, so it's already burned. So that now the burning rate is controlled by the rate at which the mixture becomes available for burning. Yeah, so the rate of burning is controlled in this phase primarily by the fuel air mixing process. Yeah. Wait a moment. All right. Yeah. So we will see here that we have two combustion phases. Yeah, two combustion phases. So the first one is the premix combustion phase. It means that it will burn all the mixture that has been formed in the ignition delay. Yeah. While the second one is the mixing controlled combustion phase. It means that this is said to be mixing controlled. It means that we can control the combustion phase here. Yeah. So the rate of burning is controlled in this phase primarily by the fuel air mixing process. So that when we want to control this, yeah, we can control the fuel injection. Yeah, so when we control the fuel injection to the process, to the burning process in the cylinder, so this is what we perform. So we only control the second phase of the combustion. So what happened in the first phase cannot be controlled. Yeah, so it occur naturally because it's already mixed. Yeah, in the ignition delay. So we cannot control this one. What we can control is only the second phase of the combustion. Yeah, and last is the late combustion phase. So in here we have heat release. Yeah, heat release may proceed at a lower rate well into the expansion stroke. So no additional fuel injected during this phase. Yeah, so there will be no fuel injection again. So the injection is only occurring starting from here up to here. Yeah, and what we can control here is in the mixing controlled combustion phase. And here there are no fuel injected. What is only burning the rest of the fuel. Yeah, so combustion of any unburned liquid fuel, and soot is responsible for this. Yeah, why we have soot? Soot. What is the meaning of soot? SOOT. 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 What is it in Indonesia? Anyone knows? Soot.
Jelaga ya.
Ya, correct. Ya, jelaga. Jelaga itu apa ya?
Hitam-hitam ya.
Iya, betul.
Kayak flag hitam.
Ya, betul. Ya, jelaga ya, hitam. Biasanya warnanya hitam ya, pengotor yang berwarna hitam ya. Ya, jadi ini so soot ya is formed in the late combustion phase. Why? Because the temperature is already low, yeah, quite low. The pressure and the temperature is already dropped, yeah, is already dropped, so that the combustion process occur at a relatively lower pressure and temperature. So that will produce soot, yeah, soot or jelaga, yeah. Oh yeah, wait a moment. Right. Okay. So we have 4 phases here. Yeah. So we understand the difference. Yeah. So first here is the ignition delay, and afterward we have the premix combustion in which we cannot control the pressure sharply increase. Yeah, it's naturally occur because there is a premix of fuel and air before. Yeah, and then 3 here is the phase in which we can control this by adjusting the fuel that is injected to the cylinder. And afterward from 3 to 4 here it drops again. So this is already the power stroke, yeah, in which this is the phase of the late burning, yeah, of the rest of the fuel. Yeah, so this is the stages in CI engine. Yeah, and this is another graph in which we have now in the ordinate here we have the m dot of the fuel, yeah, and this is shown by the dash dot line here, yeah, the dash dot curve here, and then we have the heat generation, yeah, the heat generation or heat addition, yeah, heat addition because of the burning process, and P here is the pressure. So this is similar to what we have before. So yeah, actually here we have the mass flow rate here. Yeah. So if this is the top dead center, yeah, here. So the fuel is injected here. Yeah, the fuel is injected here. Sometimes, very close to the top dead center or a little bit afterwards. Yeah, so more or less is here. And here we have the black line here, the solid line here is Q dot. Yeah, so this is a heat addition. Yeah, heat addition to the cylinder. So we have the burning process here, in which this is the start of combustion. So the start of the combustion here is when we have the peak increase in heat addition here. Yeah. And we see the heat addition here is the sharp increase here, and afterwards we will have the rest here. So here, yeah, we see the heat addition afterwards. Yeah, after the premix combustion process here is not as large as this one. Yeah. All right. So that will be the process NCI engine. Yeah. And we can also see the heat release here. Yeah. We have the ignition delay, similar to before. Yeah, this is more or less similar. We have the ignition delay, and then we have a premix combustion phase. Yeah, in which here we have the, so this is actually the enlarged view, yeah, of the previous graph. We have a very sharp increase here, in which this is the premix. We cannot control. Yeah, so this is naturally occur from B to C, which is premix combustion, and then we have the mixing control combustion phase here. Yeah, and which here is the end of the injection. So it can be at the top dead center or a little bit afterwards, after it, after the top dead center. So here is where we can control, by, for example, controlling the flow rate of the fuel and also the timing here. So this will change this phase. Yeah, this will change this phase, but this one cannot be controlled. Yeah. So here is a mixing control combustion phase, and afterwards here we have the late combustion phase. Okay. And for CI engine, the air fuel ratio is about 18 to 70. Yeah, so much larger. Yeah, the air, it means that it's the air fuel ratio is larger than the SI engine. Yeah. And here is it to be that the mixture is highly non-homogeneous, because we don't mix the fuel with air before, but instead the fuel is ejected. Yeah. All right. Any questions before we continue?
Ma'am, excuse me, ma'am.
Yes, Sultan.
I just wanna make sure about something about premix combustion, right? Uh, ini premix combustion phase. So it's basically like spark light, ma'am. It just to start the ignition, right, ma'am?
Yes.
Kalau misal maaf pakai bahasa Indonesia, jadi kalau misal ibaratnya itu auto cycle, itu ibaratnya premix combustion phase itu kayak nge-sparklingnya nggak sih, ma'am?
Yeah. So that is the start of the combustion. So I will show you again our previous slide. Yeah. This is to. Yeah. So when we have here. Wait. Okay. So this is the the phase that we have in auto cycle. Yeah, this is a phase that we have in auto cycle. So we also have the ignition lag here. Yeah, so perhaps ignition lag here is similar. Yeah, almost similar to the ignition delay in the diesel cycle. Yeah, in the diesel engine. Yeah, and afterwards we will have the propagation of the flame, in which P here, if you see here. So this is the pressure increase attached. So this is starting to the flame is started, yeah, at point B. So the flame is started up until the maximum pressure reach, yeah, and afterwards we will have the after burning process. Yeah. So if we see here that the first stage here is similar, yeah, in SI engine is similar to ignition delay. And the propagation of the flame here is almost similar to what we have in the premix combustion phase. Yeah, in which in premix combustion phase we cannot control, but afterward here for the third phase here is slightly different because we have a controlled combustion phase. Yeah, so we still have the controlled combustion phase, while this is already after burning process in SI engine. Yeah, so yeah, more or less similar. Yeah, so here from B to C of what we see in SI engine is almost similar to here. Yeah, to what we have here from point start of combustion here to the maximum point here. Yeah, so it's almost similar. But the difference is when we already reach the maximum pressure here, we still can control the combustion process. Yeah, for CI engine. So it means that we still have the combustion process at this stage, while in SI engine it's already after burning process. Yeah, so after reaching maximum, so it's after burning. Yeah, okay, because here we still give fuel. Yeah, so we still in CI engine we still give fuel after the top dead center as shown here. Yeah, we still give fuel. We end the injection after the top dead center. So in this phase, this is the mixing controlled combustion phase. And the after burning or the late combustion phase here is similar to the after burning process in SI engine. Okay. Yeah, so yeah, more or less similar, yeah.
Okay. Thank you very much, friend.
Okay. All right. Any other question?
Excuse me, ma'am. Can I
Yes.
ask? Okay. Okay, ma'am. I just wondering, like submarine that use low speed diesel, it's submarine is like use dual cycle. It's like mine.
Yeah, no, yeah.
Because it use diesel, it means the submarine still use Satan full, man. Satan fuel.
Yeah, yeah. So yeah, actually, yeah, diesel is dual cycle engine. Yeah, it's still included in diesel engine. Yeah, so dual cycle engine is still included in diesel engine. Yeah, so it's basically diesel engine. So use diesel fuel. Yeah.
Okay, thank you, ma'am.
Yeah. Any other question?
I want to ask about glow plugs. In the slides of the component of CI engine, there is a component that is glow plugs. In the combustion, if there is a glow plug in the engine, then how it affects the combustion process in the combustion stages.
Yeah, glow plug is sort of pre-ignite. Yeah, pre-ignite the fuel before. Yeah, this is a nice question. Yeah, so here we sort of have a pre-combustion chamber here. Yeah. Mhm. Yeah. do we have it here? Wait a moment. I'll check it. Yeah. We have it here. Yeah. So we will discuss about this. Yeah. So that will answer your question. Yeah. So we will continue a bit. So for a few slides here. Okay. So that is a good question. Yeah. Okay. Before I answer your question, so I will continue a bit here. So there are basically, yeah, based on the injection, there are two types of CI engine. Yeah. So the first one is the direct injection, in which here the fuel is injected directly to the cylinder. Yeah. Injected directly to the cylinder. So here we have usually use this for very large engine, as in the power plant. Yeah. So in diesel power plant or stationary power plant, yeah, we use that direct injection. Yeah. And this is usually designed when we have a low engine speeds. Yeah. The time, because the time available for mixing is long, yeah, because it's quite slow, so that a direct injection in swallow or short, yeah, short chamber is used. So this is used for open or shallow ball in piston. Yeah. So this is very, the size of the engine or the diameter of the engine is large. Yeah. When the diameter of the engine is large, the bore diameter is large, we can use this direct injection. And as the engine size decreases, yeah, when we want to reduce the bore diameter of the cylinder, and we want to increase the engine speed, yeah, because to reach a certain compression ratio, when we have a smaller cylinder, it means that the stroke should be longer, yeah. The stroke steps should be longer, so it means that the engine speed increases, yeah. So that we want to, when we use direct injection, so that we have to think about how to increase the amount of throw, yeah, to promote better fuel air mixing, yeah. So this is what we can do in the design if we use the direct injection. Now, regarding your question before, when we have a glow plug, yeah, or we have a pre-chamber, so we have another region, yeah, before the cylinder. Yeah, so this is called indirect injection. Yeah, when we have an indirect injection, so that the chamber is divided into two regions, and the fuel is not directly injected to the cylinder, but instead it's go to the pre-chamber, in which it will have, yeah, like what we have seen before, it will have a glow plug. Yeah, it's connected to the main chamber through a nozzle or orifice. Yeah. So that if we have a small high-speed engine, like in the car, in which the chamber wall is not sufficient, so we can use indirect injection, where high swirl or turbulence is generated in the pre-chamber during compression, and products or fuel blow down and mix with main air chamber. Yeah. So this is the case, yeah, in which yeah, we have here, for example, here we have a direct injection in a quite shallow chamber. Yeah, so for a short, for a large diameter and quite short clearance area here. Yeah, so it's close. The distance here to the end of the cylinder here is quite close. So this is a quite shallow, yeah, shallow bulb. So here we can use direct injection. Or if we have a deeper, yeah, if we have a deeper one, so we can use roll. So this is directed at a certain angle, yeah. So a certain angle here to promote roll inside, yeah. So although this is quite shallow, quite deep, yeah, quite deep or quite long here, but with the swirl generated here, with the angle here, the swirl will be generated, so it can promote mixing, yeah. And this is the question before, what if we have this one, yeah? So we have the glow plug here, and we have the orifice plate. Yeah, we have the RF substrate, and then it will be injected. Before. Yeah, so we see here that here we have the turbulent and swirl pre-chamber. Yeah, so the main thing here is that here we use that pre-chamber to generate swirl and turbulence. Yeah. Okay, so we see here that yeah, this is the photograph. Yeah. Wait a moment. Yeah, so we will see here that in the slide here, yeah, we have a direct injection, which is quite it's small, shallow, yeah, shallow chamber here. So we have a combustion process here, and this is with direct injection multi-hole nozzle. So we have several nozzle here at a certain angle, so it will produce swirl inside. So you can see here that there will be swirl, yeah. So this is also to promote turbulence. And here we have only single injection. So you can see here is only one here on the side. Yeah. So you see it, this is not as good as on the left, on the middle, on the left here. Yeah. So it's better here. It's only one. So it started from this end, from the sides near the injection. Yeah. While here multi injections better, will be better in terms of the combustion process. And here is the indirect injections role. Yeah. So what happens here is that when we have a pre-chamber, it means that the fuel is not directly injected there, but it will be injected in the pre-chamber, and then it will go into sort of a nozzle or orifice. Yeah. And then it will be already have swirl there, and then it will be released to the combustion chamber. Yeah. And what is the function of the glow plug? Yeah, so basically is to condition the fuel before it goes into the cylinder. Yeah, so basically it's going to hit it. Yeah, going to hit. Yeah, going to hit the fuel before it goes into the the cylinder. Yeah, so this is for swirl pre-chamber. Yeah, we have another chamber there. Yeah, so the idea is to, yeah, basically to increase the turbulence. Yeah, to increase the turbulence, to promote mixing. Yeah, because we don't do mixing before. Yeah, so we don't have mixing before, so it's directly injected. So turbulence here is very important. Yeah, so the purpose, yeah, the purpose of the pre-chamber, in which usually the pre-chamber is occupied with glow plug, yeah, is to condition the fuel, yeah, before it goes into the cylinder. Yeah, so to condition the fuel, this means that to increase the intensity, the turbulence intensity, to increase the swirl, and also to increase the glow plug itself, to increase the temperature. Yeah, so it becomes hotter. Yeah, at higher temperature, it will be vaporized easily. Yeah, at higher temperature, so that it will be burned easily. Yeah, so that will be the explanation, Antim. Yeah.
And thank you, Kim.
Yes.
I just wanna ask something related from Atim's questions. So when we have the another chamber heat to hit the fuel, what the difference between the indirect injection with dual cycle, man?
Yeah. Dual cycle is the heat addition is performed. Uh, yeah. Yeah. Yeah, so the heat addition, okay. Okay, this is a tricky question. I will not answer it first. Yeah, so I will try. I will try to read first. Yeah, I will not answer it now. Yeah, I will check again. Yeah, I will check again on that. But usually this indirect injection like this one is used um, for small engines. Yeah, in which a dual cycle is usually used in large engine and low speed. Yeah, so yeah, so this one is usually uh, in higher speed. Yeah, a small engine, higher speed. Yeah, for indirect injection like this one. Um, yeah, but I will check again. Yeah. Um, I will check again on that. Yeah, I will check again on that. I will not answer it now. Yeah, I have to make sure that yeah, my answer will be correct. Yeah.
Ma'am, thank you, ma'am. Because I confused about when I see the graph for dual cycle, it's the process is nearly like that, ma'am. So I'm confused about the difference about them.
Mm. So
Okay,
the
thank you, ma'am.
process, yeah, for the dual cycles, the process is almost similar to this one with pre-chamber. Yeah. Yeah.
Yes,
Is
ma'am.
it? Okay. Yeah. All
Yes.
right. All right. So I will check again. I will check again. That may make sense. Yeah. But I will check again whether uh, is it correct whether the dual cycle will always use pre-chamber or not. Yeah. I will check again on that. Okay.
Ma'am, thank you very
Okay.
much, ma'am.
Inshallah. Yeah. Inshallah. Okay. Any other question? All right. Okay, so we will continue again here. So this is about the combustion characteristic in which because we inject the fuel, yeah, when we inject the fuel, so that means that we will have the flow of the injection, and then also the burning process will depends on the injection of the fuel, yeah. So that here we have yeah, so this is not this is just to oh, sorry, so this is just to make you uh, know, yeah, that we have uh, the equivalence, yeah, sorry, here we have the fuel air mixture before and during the combustion phase, yeah. In general, most of the combustion occurs under very rich condition within the head of the jet. Yeah, so this is depends on the injection. Yeah, very close to the injection, we will have the combustion started. So the combustion started at very rich condition, very close to the fuel injection here, close to the jet. And this produces a considerable amount of solid carbon or soot, yeah, as what we seen before. Yeah, soot. Yeah. And this is the liquid. So if we look at here at the graph here, we have uh, uh, the 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 fuel. Yeah, so this is the fuel development when it's injected. Initially, all of that will be fuel, and then we have a mixture around it. Yeah, a mixture around it when it's injected in the cylinder. Yeah, and afterward this will start to flame. Yeah, to start to burn. So we have a flame here. Yeah, and so on. Yeah, so that we have a flame, and at the area further away, yeah, further away from the center here, yeah, away from the center, so that will cause soot, yeah, soot. Yeah, so we see here that the high concentration of soot here occur at the area further the farthest area, yeah, the farthest area from the injection head. Okay. So we will see the explanation of ignition delay here. So you can read of this. Yeah, it's Azan time. So we will take a break for 2 minutes. Yeah, so you can read on this. Okay, are you still here? Okay, we will do a brief check for you who is still here. You can raise your hand. Yeah. You who still here, you can raise your hand. Okay, Ratno, you hear it now?
Yes, ma'am.
Okay. Salwa? Salwa, you hear? No? Okay. Yusuf?
I'm sorry, ma'am. My Wi-Fi is unstable.
Okay. All right.
Yes, ma'am.
Yeah. Okay. Just checking. Kinting, you here?
I'm here, ma'am.
All right. Okay. All right. So you can lower your hand. Yeah. Okay. Just to check whether you still here. Yeah. All right. Okay. Thank you. Now we will continue on the explanation, yeah, for the phases that we have learned. Yeah. Now we have the ignition delay, which is the first phase in the combustion process, yeah, for the compression ignition engine. So we will see here that ignition delay here is the time of the crank angle interval from when the fuel onset of combustion. So onset here means the start, yeah. So if we have the term of onset, so means the start of the combustion, yeah? Onset or start of combustion. So what happens here, why there is a delay? Because we have some physical processes that should be performed before it can be burned, yeah, such as what we have discussed before. Yeah, there is atomization, evaporation, and also mixing of fuel vapor with the air. Yeah. So what are the factors that affect these physical processes? Yeah, if we talk about atomization, so this will depends on the injection pressure. If we have higher injection pressure, so it means that the fuel will be easier to atomize. And also, if we have smaller injector hole diameter, yeah, smaller injector hole diameter means that the velocity, yeah, the velocity will be higher as well. So that will make the fuel easier to be atomized. Yeah. And also here we have the fuel viscosity. Yeah, the fuel viscosity. This will affect the atomization as well, and the cylinder pressure. Yeah, cylinder pressure. And the rate of vaporization, the second factor here, depends on the droplet diameter. Yeah, so the droplet diameter will depends on also the structure or the shape of the injector. Yeah, and also the velocity, the fuel volatility. Yeah, how easy is it for the fuel to be vaporized, yeah, and to be burned, the pressure and the temperature of the air. Yeah, of course, if you have higher pressure and higher temperature, so that will be easier to be evaporated. And aside from the physical processes, this depends also in the chemical processes. Yeah, so this is very similar to auto auto ignition phenomenon in premix fuel air. Yeah, only more complex since this is non-homogeneous, or we can say that to be heterogeneous reaction. Yeah. So yeah, we see here that there is a combination between the physical process and the chemical processes. That's why we have the delay. Yeah. So when we inject it, we don't get it burned directly, but we need some time. Yeah, right. So these are the factors. More detail. We have the injection. Yeah, because we have the delay, so that we have to set the injection timing. Yeah, when to start the injection. So this is typically around 10 to 15 before the top dead center. Yeah. And also the injection quantity. For a CI engine, the air is not throttled, so that the load is varied by changing the amount of fuel injected. Yeah. So again, the air is not throttled. Yeah. So that what we control here is the amount of the fuel which is injected. Again, here increasing the load. Yeah. If we have increasing load or increasing break main effective pressure, this increases the residual gas and wall temperature, which result in higher charge temperature at injection, which translates to a decrease in the ignition delay. Yeah. So if we have higher load, higher BMEP, it means that we have higher temperature, yeah, higher pressure, higher temperature, and that with higher temperature, it means that we have shorter delay. Yeah, shorter delay, of course. Higher temperature, it means easily to be burned, easier to be burned, so that the ignition delay will be shorter. And also, of course, the intake air temperature and pressure. Yeah, so that when we have higher temperature and pressure, so that we will have shorter ignition delay. And also because we talk about pressure, so this also relates to the compression ratio. Yeah, if we have higher compression ratio, it means that at the end, the pressure, yeah, from the motoring process, the pressure will be higher as well. So of course, this will make the ignition delay shorter. Yeah, so this is the factors. And when we talk about fuel ignition here, because this is very important when we talk ignition delay, so that the fuel quality now relates to the ignition delay. Yeah. So we see here that what is the SETA number? Here you already discussed that in the assignment. Yeah, in the assignment. Now, before we talk about this one, I want to hear from you what you have found about SETA number. Yeah. Yes.
Can you hear my voice?
Yes. Sultan.
Okay. I will try to answer about the SETA number. The SETA number is the same, the percentage, the ratio, but it's between the N hexadecane with mixture of N hexadecane and one methyl naphthalene. Methyl naphthalene, ma'am. And it's about and same with octane number, it's related with knocking. So higher percentage of the ratio will decrease the knocking.
Okay. Yeah. Okay. Any other?
Ma'am, excuse me, ma'am.
Yes, Edgar.
I want to give additional in DIN 5177773, a field with a certain number of 50 exactly as ignitable as a mixture of 50% of cetane and 50% of 1 methyl naphthalene instead of 1 methyl naphthalene heptamethylononane.
All right.
Yes.
Okay. Yeah, thank you. Yeah. All right. Okay. Yeah, so I think you get that correct already. Yeah. So actually, what is the SETA number? Yeah. Yeah, so this is to quantify the quality of the fuel, yeah, for the diesel engine, or we call it as diesel fuel. So when we have the low Saturn fuel, we will read from this slide first. Yeah, for low Saturn fuels, so that the ignition delay is long, And because the ignition delay is long, most of the fuel is injected before auto ignition and rapidly burns. Yeah. So because the ignition delay is long, most of the fuel is injected before auto ignition and rapidly burns. Under extreme cases, this produces an audible knocking sound referred to as the diesel knock. Yeah, so it's similar. Yeah, when we have auto ignition, it means that we will have knocking. Yeah, and this can occur as well in diesel engine. If we have high Zeton fuel, so that the ignition delay is short. Yeah, when the ignition delay is short and very little fuel is injected before auto ignition, the heat release rate is controlled by the rate of fuel injection and fuel air mixing that cause motor engine operation. Yeah, so that this is dealing actually with the phases that we have. Yeah, the phases that we have in the combustion process for the diesel engine. Yeah, so we have the ignition delay, and afterward we have the premix combustion phase, and then afterward we have the mixing control. Yeah, the mixing control rate. So that when we have the low Zeton fuel, low Zeton, so that the ignition delay is long. Yeah, the ignition delay is long, so that there will be too much fuel. Yeah, too much fuel that is injected before the combustion started, and once the combustion started, so there will be too many fuel, and that will cause the combustion occur in many places. Yeah, and that cause knocking. Yeah, when we have high Zeton fuel, it means that the ignition delay is short, so that when we injected the fuel, yeah, only a little fuel is injected during the ignition delay. So then when it's automatically burned in the premix combustion phase, yeah, so the amount of fuel that is burned is still little, and most of the fuel is in the mixing controlled phase. Yeah, so when we have the mixing control phase, the fuel is in that phase, injected in that phase, so that becomes an advantage because we can control the combustion process, and we can have a smooth operation. Yeah, so that when we talk about Zeton number, so it's dealing with the ignition delay, whether it's short or long. Yeah, and what we want to have is a short ignition delay. Yeah, so it is correct. Yeah, so this is between, or we can say that to be isocetan, yeah, or heptamethyl, and has a Zeton number of 15, yeah, and Zeton here, which is N-hexadecan, has a value of 100, yeah, or we can use that as zero value is actually methyl naphthalene. So we will not focus on that, yeah, because this is very chemical, yeah, and very difficult name, yeah. But the main thing is that what we want to do with the Zeton number is that this is analog to the anti-knock quality using the octa number. Yeah, so that when we have higher Zeton number, then we have a better ignition quality or shorter ignition delay. So that basically the Zeton number will be calculated at the percent of hexadecan and about 0.15 of the percentage of the heptamethylnonan. Yeah. Okay. Yeah. So this is the original one is that one, and this is replaced with HMN, which is more stable compound. But aside from that, is that we can also measure that Zeton number. Yeah, with the same method as before. We have the variable compression ratio engine, in which here we specify the operating conditions. Yeah, we specify the inlet temperature, the rotational speed, the spark advance. This one is similar, and now we specify the injection pressure, which is 10.3 megapascal. Yeah, and here. Yeah, so that here with this test, yeah, we can find the certain number of the fuel. Yeah. So this is the representation of the certain number, in which this will be there will be a inverse correlation, yeah, between octane number and certain number. Yeah. So that if we look at here, if we have a high certain number, yeah, if we have a high certain number fuel, so that will be that will have a low octane number. Yeah, that will have a low octane number. So that means we cannot change the fuel. Yeah, we cannot change the fuel. For example, you want to add text light into a diesel engine, so that is not possible because the characteristic is very different. Yeah, so the gasoline is a poor diesel fuel and vice versa, so that we cannot switch that. Yeah, we cannot switch that because the characteristic is different. Yeah, so what we want here is that to have the ignition delay as short as possible. Yeah, while that cannot be obtained in high octane number fuel. Yeah. Okay, so this is the characteristic of the fuel for the diesel fuel. Yeah, the diesel fuel particularly. Okay, so this is to answer the question in assignment. Yeah, so why we need to give a certain fuel? Yeah, because the characteristic is very different. Yeah, because of the difference in the combustion characteristic. Okay, so then now we continue to the performance. Yeah, we will see the performance of the diesel engine. Yeah, basically it will have the approximately the same trend line. Yeah, for the internal combustion engine. We have the torque which is increasing, and then it will reach a maximum and go down again. Yeah. Now be careful. This is as a function of load. Yeah. So not as a function of engine speed. So you see here, this this chart is slightly different to what we have seen before, because now the engine speed is held at constant. Yeah, constant value, which is 1500 RPM. Well, the x-axis here is the load. Yeah, the load. So we see that the torque is getting higher with the load, and also the BSFC here, maximum at very low load, low load, and then it's going very high at low load, and then it's decreasing and going up again. Okay, and this is the exhaust gas temperature here. Yeah, so this one is the exhaust gas, and then here we have the power output, the brake horsepower here. Yeah, shown here. So it's increasing, and then it will get a at 100%. So it will increases a lot, increasing to the maximum. Yeah, because this is up to 100% load, so the maximum load that can be achieved. And then the BMEP is also increasing. Yeah. Okay, this is as a function of load, and this is a function of RPM. So as a function of the engine speed, this will be similar to what we have in the gasoline engine. So basically similar graph, similar trend line. Yeah. But there is a difference on the value. Yeah, depends on the size of the engine as well. And one thing is that the air is not throttled, yeah, inside the cylinder, but it's more common to use a blower, or here we can use the turbocharger, yeah, in which the turbocharger is actually to add more air, yeah, inside the cylinder, yeah, in which we have here a compressor, yeah, a compressor to give a charge into the cylinder. Yeah, so we have a compressor here which is connected with the turbine. So this is called the turbocharger. yeah, in which this compressor is driven by the turbine, and this turbine is driven by the exhaust gas. Yeah, so when we have the diesel engine and then the gas release here, yeah, is released through the exhaust valve, and then because the temperature is high, yeah, so that we can and also we have a quite large compression ratio. Yeah, it means that we have a large flow rate of air as well. So we can use that to drive the turbine. Yeah, we can use that to drive the turbine, and this turbine will drive the compressor and further increasing the air, flowing the air into the cylinder. Yeah, so this is for engine with turbocharger. So this is how it looks. Yeah. So when we use turbocharger, because we have we have the compressor here. Yeah. So this is one. We have a compressor inlet. So this is a turbocharger, and this is the engine. Yeah. So when we have a turbocharger here, we have a compressor here. We have a compressor inlet, and then we have the compressor discharge, and then here we have the charge air cooler. Yeah, sometimes we have to limit the temperature of the air. Yeah, so yeah, of course, if the temperature is higher, it will make the ignition delay shorter. But when it's getting too high, so that we have to reduce the temperature. Yeah, so that we have an air cooler here. Yeah, and so on. Okay, so this is similar. Yeah. Okay, so I think that will be for the explanation for the diesel engine. Yeah, and we have a slightly different shape here in which we have the supercharger here. It looks like gear, for example, here. Yeah, so we can use that as well. So this is called root supercharger. Okay, so this is for diesel engine. Yeah, where we can have additional part. Yeah, similar to this one as well. Yeah, to reduce the temperature. Yeah, we can have air cooler or we can use intercooler like this one. Yeah. Okay. And also we can use a combination between turbocharger and the supercharger. Yeah, so this is for a very large diesel engine. Usually it such as that use in the plant, for example. Yeah, so we can use turbocharger and also combination with true supercharger. But of course we have to check for the temperature, yeah, so that it's not becomes too high. All right, so I think that is for the diesel engine. Yeah, is there any question? Okay, if there is no question, I would like to give a practice first before we close this class. Yeah, so we will have another practice for the performance calculation. Yeah. You can look at the book. Yeah. If you have the book already. Yeah. So okay, so we will look at the book here. We will try to practice another one here, which is about the performance. Yeah. Performance calculation. So what about the performance calculation? It will be similar, yeah. Whether you use the diesel or Otto cycle, in terms of the performance calculation, it will be different. Now I will try to give an example in the book, which is in example 3.4. So you can see that in the book. Last week we already discussed 3.2. Yeah, now we will discuss 3.4. And when we here we have a gasoline engine, and this is known to be 4-stroke. Yeah, and this is 6-cylinder. Yeah, so gasoline engine, which is 4 strokes, 6 cylinders, and this is working at a rotational speed of 4,500 RPM. And the torque here, which is produced here, is known to be 23.5 kilogram force meter. And it's known that the ratio between the ratio of S over T is 1.2. So I would say that's to be stroke, yeah, stroke over the bore diameter. Yeah, bore diameter is 1.2. Yeah. Right. Now the question is A, find the effective, yeah, the effective motor power. So that will be the brake power, the brake power. And then B, we want to find the indicative power and the friction power. If the mechanical efficiency is 80%, yeah. And then C here, we want to find the PMEP, the brake mean effective pressure, and IMEP if the bore diameter is 90 millimeters. And D here, and D here is the SFC, yeah, the specific fuel consumption if the total efficiency, yeah, the total efficiency is 28%, yeah, and the lower heating value is 10,000 kilocalorie per kilogram. Yeah. And E is the amount of fuel per hour. Yeah. M fuel per hour. Yeah. So this is the question. Yeah. So that how to find this, how to answer this. Yeah. We will look at here. The first one is finding the brake power. Yeah. So finding the brake power. So the brake power here is the easiest because this is based on measurement. Yeah. So when we have the torque, yeah. So power, yeah. So brake power here is torque times omega. Yeah. Yeah. So that will be the brake power. So that if we have the torque, so that we have 2 pi n over, if it is in minutes, so that we can change that to 60. Yeah. And for the torque here, make sure that we convert the unit. Yeah. So it depends on us which one that we want to use. Yeah. If we want to use it in SI, so make sure that is converted. Yeah. So when we have T already, yeah. the torque so that we can convert it to SI, for example. And then we have 2 pi times N, and here is the rotational speed. Yeah, so that will be 4,500 RPM. So that's to be per second. So that's divided by 60. All right. So that here is we have the brake power. Yeah. Now question B is to find the indicative power. So how to find indicative power? Yeah, how to find the indicative power?
Indicative efficiency.
Yeah, using efficiency. So we know that efficiency, the mechanical efficiency is PB over PI. So that if we know PB already here, yeah, so that we can find PI, which is equals to PB divided by the mechanical efficiency. So that now we have PI. And how to find PF here, the friction power?
Indicative power minus brake power.
It's correct. Yeah. Indicative power minus brake power. So we have that already. Okay. Now question C is, now this one is new. How to find BMEP? So how to find BMEP? So BMEP is basically the work, yeah, the total work, the work divided by the volume. Yeah, the volume, the volume. Or just write it down as VD, the volume, or you can just write it down as V, yeah, the volume. So that the work here, yeah, is equals to the power, yeah, the power multiplied by NR over ED times N, which is the rotational speed. Yeah. And here, or you can write it down as N capital because this one is using small. I'll just write it down here as N small. Yeah, so that will be N, like this one. So this is the rotational speed. Or we can write it down as, because the power here is this one. Yeah. The power here is this one. So that we have T times 2 pi N. Is it? Over 60. Yeah. And this is the NR here. It depends on whether it is two stroke or four stroke. Yeah, or four stroke. And this is divided by VD. VD is the volume. Yeah. VD is the volume, and this is multiplied by N. Yeah. Okay, so that will cross that out. We should check for the unit, yeah, whether this is if this is in RPM already, yeah. So that will be cross. So that will be is the same as this one. It will be cross. So I will erase that. So that will be 2 pi N, yeah, because we will erase that. So that will be gone. Yeah. So that will be T times the torque. Yeah, we have the torque times 2 pi times NR divided by VD. And this is 4 stroke. So 4 stroke here, yeah, for 4 stroke. So that this will be 2. Yeah, that will be equals to 2. So NR equals to 2. Yeah, because this will be, yeah. Okay. Okay, so this is correct, yeah? All right. So that now we can find the volume, yeah? So that now we need to find the volume. Do we need the volume? We know the bore diameter, yeah? We know the bore diameter. So the volume here will be the stroke volume. Yeah. So that will be quarter pi d, the bore diameter, squared time the stroke. Yeah. Yeah, sorry, it looks like it's been disconnected and all of the writing has gone now. Yeah, where were we? All right, we will continue. Yeah, we will continue a bit. It looks like it's been disconnected and the whiteboard has gone. Yeah. So we will see again that we will continue the calculation. Yeah, in which PMEP before, yeah, is equals to the torque times 2 pi nr divided by the volume. Yeah, divided by the volume. Now, the volume here we can calculate it with quarter pi d squared. Yeah, quarter pi d squared times the stroke. So we have the stroke here, which is 1.2 of the diameter, so that we can find the volume. And once we have the volume here, and this one is 2 because we have 4 stroke, so then we can calculate the BMEP. Now check again for this calculation. Yeah, check again. Okay, so that should be the BMEP. And if we want to calculate the IMEP, now we can directly use it from the pressure, the power that we have, PI times NR over VD times N. So from this, we can calculate as well. So this one is similar. You can calculate it from this one or from the brake power that we have already. Yeah. Okay. And that afterward, we can find question D, which is specific fuel consumption. Yeah. If we know the total, yeah, the total efficiency is now to be 28%. Yeah, 28%. So that we can calculate the M dot first. Yeah, M dot first. So that we can calculate the thermal brake efficiency that will be PB over M dot times the lower heating value. The one that is known is the lower heating value. So that we can calculate this one. We have the value of lower heating value. Yeah. And we have also PB. Now, this one is already known. Yeah. So that we can calculate M dot fuel. Yeah. And once we have M dot fuel, then we can calculate SFC. So FSC is M dot over PP, or that one is actually M dot over PP already. Yeah. Okay. Okay. So that is for T. And E is finding the mass flow rate. So once we have this one, we answered E already. Yeah. Okay. So I think that is all. Yeah, so by looking at this, we have efficiency of break thermal heat should be 1 over SFC. Yeah, SFC low heating value, such as this one. So if we want to find SFC here, that will be equals to, check for the units. Yeah, that will be equals to 1 over the thermal efficiency times LHV. Yeah, but check for the unit first. Okay. All right. So I think that will be all. Yeah. For example, now the important thing here is that we can calculate PMEP. Yeah. Okay. So I think that is for all for today. Now, yeah. Any question? Yeah. Is there any question? Okay. Right. Yeah, if there is no question, we will continue again next week, inshallah. So this will be the end of the class. Thank you, and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you.
Thank you, ma'am.
Thank you,
Thank you,
ma'am.
ma'am.